Watch a top student tackle a math exam. They deflect basic algebra, slice through geometry, and parry calculus. It looks like total mastery. Rote memorization works for the bottom 80% of test questions. If you know the formula, you plug in the numbers and collect your points. The test is simply checking if you remember the rules. Then comes the final 20%, the exemplar problems. These questions are engineered specifically to break the memorization loop. This diagram shows what an exemplar attack actually looks like. Sine theta plus cosine theta equals 1. If you try to force standard trigonometric identities into this, they bounce right off. There is no immediate formula to plug and play here. Overcoming this requires a strategic thinking process. Instead of forcing a formula, you analyze the structure. Squaring both sides produces the identity sine squared plus cosine squared plus 2 sine cosine. Since that first part equals 1, the entire problem simplifies to sine 2 theta equals 0. You cannot memorize your way to a perfect score. Closing the margin between good and excellent demands strategic deduction. The first step in this thinking process is entirely passive. You stop calculating. You observe the variables and define the exact limits of the mathematical battlefield. This number line graphic maps out how to exploit an absolute value problem, like the modulus of x minus 2. A modulus function looks intimidating until you define its limits. At exactly the number 2, the function splits cleanly into a negative interval and a positive interval. Once you define the boundaries, you reach step 2, transforming an overwhelming enemy structure into a form you already know how to defeat. Take a look at this unstable complex number fraction, 1 plus I divided by 1 minus I. Fighting this division problem head-on creates a mess of algebraic dead ends. We bypass the complexity by striking its structural core. We multiply top and bottom by 1 plus I, rationalizing the denominator. Forcing this multiplication collapses the messy fraction entirely. The denominator becomes a clean integer, leaving a vulnerable I, or 0 plus 1i. The math itself did not get harder. We simply reshaped the equation, forcing the problem to fight on our terms. Some problems scale infinitely. To conquer a chain of numbers that never ends, you use a specific 3-strike sequence, the principle of mathematical induction. This logic graphic illustrates the first strike. You prove the base case. You test the math to ensure the logic holds true and locks into place when your variable, n, equals exactly 1. Strike 2 makes an assumption. The proof holds true for an arbitrary point, k. Strike 3 delivers the final blow. You use k to prove the next step, k plus 1. Linking them triggers a chain reaction, proving the math for all following numbers. This 3-step mechanism functions as a logical engine. By proving how one step creates the next, you solve for infinite possibilities with a single, finite proof. The final challenge shifts from calculation to pure logical structure. Standard algebra cannot solve the problem. The proof rests on the relationship between definitions rather than arithmetic operations. This flowchart visualizes a classic logical challenge. You must prove that if n squared is an even integer, then n itself must also be an even integer. Attempting to prove that directly leads into a circular trap. You dismantle it using the contrapositive method. Instead of proving the original statement, we flip the board. We assume n is an odd number. Because an odd number squared inherently results in another odd number, the initial conditions of the problem are logically impossible. The mental battle ends. The logic is sound. Reaching the top tier of mathematics relies entirely on how you approach the problem. Awaken your thinking process, and the numbers will follow your lead.